Well, let's start with the multi-story building. This multi-story building is made of beams and columns. So we are going to go to the software to run it. Here is the graphic interface. Well, first here you have some options to save, open, or import frame models and the environment. Very important, select the codes we are going to use to check or design the model. I'm going to use Eurocode, but you can also select any code from a long list of the most important codes all over the world. Next step is creating the model. You can create points, lines, performing Boolean operations, but for creating the model I feel much more comfortable using the script. Python is the language of CivilFEM, and here with this script I've created here, you can see here, I've created here some parameters with the dimension size of the model, and here some loops to create different points, different lines in X, Y and Z direction, and different areas here. So well, if I launch these commands here in my model, I'm going to display the script editor. Here, paste the commands. We can also open from here a test file and run it. If I press play, save it, so it is creating. Here you can see in the output window all the points that are being created. Then we will create with the next loop lines, here you have, and with the next loop we will create areas. So it's very easy with these loops or using the graphic interface to create the model.
Yes, as you can use parameters, anytime you can change all of them, and so you can run every time with a different parameter, with a different length of spans, with a different length of height of each column. So anything can be modified easily.
Well, the next step after the geometry is selecting the materials and cross sections. Here I'm going to select a material. Material classification is depends on the codes. I can select a concrete from the ACI code. In example, this one. Clicking OK. Well, I have this material. The default behavior is linear elastic, but I can modify it clicking here, and then instead of linear behavior, short-term load diagram. Press OK, and well, now we are going to use the parabolic law, and we have different ways to solve it with the parabolic law. The Puyu-Kusur plasticity, that is a model, special model for concrete behavior. Also multilinear elastic, if we are solving with elastic way but parabolic, or multilinear isotropic hardening. I'm going to use for the nonlinear analysis this one. And we can also add cracking behavior. Here the cracking behavior, clicking here we add the cracking properties we will see later in the nonlinear analysis. In my case, I'm going to leave here linear analysis, and the next step is creating sections, cross sections by dimensions, and adding reinforcement and so on. Well, and creating the mesh. I'm going to open the model, not to waste a lot of time creating the model. And well, this is my model. It's being open. And well, here entities we have these materials, concrete and steel, these cross sections. I'm going to plot one of them, reinforcement bars, and different structural elements for cells, beams and columns. Okay. Well, here we have defined also, after defining the model mesh, we define loads, different loads groups. What we've done is creating the following load cases. live loads, spectral, and dead load. Here we added the spectra and well, different loads. We can plot them here, the load on the mesh, so we can see here the arrows of the different forces we have and pressures. We can plot the other one, load, that is here in the different stores, and well, the different data. Then after defining them, we press here solve it. It's very important the name of the load cases, because the name of the load cases will be the result file names. So after solving, clicking here, we solve in elastic model way. We can open those results, and in example we have the spectral results. As we added here in the loads, the Eurocode 8 spectra, the software is performing the modal analysis. Here we have the data of the spectrum we are using. Is performing the modal analysis with the combination I select here, also the static load cases here, and after solving them I can find those results here. In example, the first mode, you open it and plot results. In example, well, displacement here, and well, here you have a mode shape. You can advance from one mode to other here, pressing this button. With different displacements. Okay, well, after solving this, we have the different load groups, and we have to combine it. The way to combine it is pressing here, selecting result files, dead load, if load, have, and spectral, and pressing OK. Then pressing OK. Here I will have the selected loads. Then I here define the name of the combination, ultimate limit state 1, press OK here, and well, I add these load cases. Here I apply the coefficients and define all the combinations. After defining the combinations, click here and the software make the combinations, saving the result files with that name. After doing that, here I open the results and I have the combinations. In this case I created two combinations, ultimate limit state 1, ultimate limit state 2, and also serviceability limit state, that is here, with different coefficients. Well, the next step is reading one of them. I'm going to read the ultimate limit state 1 and design by code. The way to design by code is using these buttons here. I can check beams, axial, shear and torsion, and cracking. I've read the ultimate limit state, so I should take axial and bending. Clicking here axial. Well, here I have the information, the active code I have, the plane I'm checking. If I'm checking 2D, this is plane X, Y, and XZ, or 3D. I check it, I'm not doing it right now, not to waste time, and well, after doing it, I create the results. Also for cells, I can design cells instead of checking, design cells, so the results are reinforcement amounts, and we can plot those results. Here, if I go to the slides.
In this case, we have selected the ACI 308 code, American code, but you can do it with any available code in CivilFEM.
So well, the procedure for this analysis is solving static response static and response spectrum analysis, combine them. So if we are performing combinations, this is linear analysis, and then in post-processing level we are designing by code. So we are solving with elastic linear behavior, but we are adding non-linear behavior in the post-processing, creating the integration diagram, taking into account this parabola rectangular law, and checking if forces and moments are inside, if we are checking our design, calculating the minimum reinforcement amount for section to be okay. And well, some results we can see here. In example, I'm going to plot from columns. I'm going to select here from the structural elements and hide them all, but also I clear the loads, and I'm going to plot only columns. Columns start in the structural element with C. So well, these are the columns. Plot them, and well, I'm going to check if they are okay or not okay. So here in the results, after performing the bending plus axial checking, this one, I can plot the total criterion. If I go closer, or well, I also can plot with these lines. We can plot in lines and with this type of plot for the criterion, or we can also plot here in the real shape with the colors. You have both options. And we can see the sections are not okay in the joint places where columns and beams join together. So we know we have to increase reinforcement there and study in detail those points. Well, the same for cells. If I, well, cells clear.
The total criterion will be related to a kind of a safety factor. Okay, if the value is below 1, it will be considered okay, and if it's above 1, will be considered that second not okay.
Well, now we are going to see ourselves or designing the cells, frames here, and well, we can plot reinforcement amount, X direction, plot.
We can use any units to plot them.
Well, here the units are square meters per meter. I don't like the units that is square centimeters per meter, the one I would like to use. And well, I can see mainly I need more reinforcement in the shear walls, more than here in X top bottom. I'm going X top, let's see X bottom. Well, now also shear walls mainly, and well, also for Y direction, bottom. Here we can see also in the slabs we need reinforcement. Well, this is the reinforcement we need. Well, mainly what we've seen is that the most important points are the shear walls and the column beam connections. So we can study in details those parts with nonlinear analysis. Well, before going to that part, as Ronald said, the total criterion that we are plotting is the ratio between the distance from the center of the interaction diagram to the action we have, these points, this distance, D1, and the ultimate capacity of the section. So the ratio between D1 and D2 is the safety factor we give. So if that is less than 1, section is okay because the action is inside the interaction diagram. If the point is outside, this is greater than 1, section is not okay. Well, after checking that, we can go further. Why should we stay there and perform a much more detailed advanced concrete modeling with the reinforcement details we got from the linear analysis that we did by code. Here we can combine some behaviors like cracking and crushing. So for tension and compression, we will have this behavior. So we will have parabolic flow for compression, which follow nonlinear compression, isotropic hardening, or Puyu-Kusud. Also could be elastic, follow this line, or if that is nonlinear, if isotropic hardening will follow straight lines. And if we have selected crushing, when we reach a maximum strain, it will break the element due to crushing, with failure to crush it. And in the same way, in tension, we can define cracking stress and also a softening modulus. And for shear, we can combine with tracker bracket shear failure.